We're going to go back and take another look at limits, but we're going to take a look at limits that may have been difficult to do in the past, and we're going to come up with a new rule to help us evaluate them. The rule that we're going to do is called L'Hopital's rule, not L'Hospital's rule. It's pronounced L'Hopital's rule. L'Hopital's rule is a very nice tool. It's super easy to use, but unfortunately it only works in specific circumstances. But the good news is we can force a lot of circumstances to be L'Hopital's rule form. First off, to do L'Hopital's rule, you need to have what's called an indeterminate form. So to use this rule, your limit has to have a specific, I missed a letter, specific indeterminate form. Now, indeterminate, there's an interesting word that we hear in math sometimes, but I don't think we necessarily know what it means. Indeterminate means we don't know what it is. Now, the easiest indeterminate form that we can think of is 0 over 0. What value is that? Now, it's very easy for us to jump out there and think that that's 1, right? Because anything divided by itself is 1. But we have another rule that kind of conflicts with that says we're never allowed to divide by 0. So believe it or not, 0 divided by 0 is indeterminate, which means we haven't determined its value yet. And actually, its value can be anything. Now, the reason that you can see that this is could be anything, because we know 0 times anything is 0, which follows then that 0 divided by 0 should be anything. Now, I know we can't divide both sides by 0 there, but you can kind of see why that would occur. All right, 0 over 0 is one of the indeterminate forms that L'Hopital's rule will work on. Also, any ratio of an infinity over infinity, so infinity over infinity, negative infinity over a positive infinity, or any way around it, any ratio of an infinity over infinity is also an indeterminate form that L'Hopital's rule will work on. So if you have 0 over 0 or an infinity over an infinity, you're thinking, hey, I'm doing a limit, I want to do L'Hopital's rule. Now here's what L'Hopital's rule says. It says if you're doing the limit as we approach something of a ratio, now it should make sense that this has to be a ratio because those are all ratios up there, that this will be equal to, by L'Hopital's rule, now we're going to use an equal sign with an L above it to show that we're using L'Hopital's rule. This will be equal to the limit as x approaches c of the derivative of the top function divided by the derivative of the bottom function. Now, be careful here. We're not taking the derivative of the original argument here. We're doing the derivative of the top separate and then the derivative of the bottom. We're not using the quotient rule here. We're just doing the derivative of the top over the derivative of the bottom. What L'Hopital's rule basically said is these two things approach whatever they're approaching, their derivatives will also approach that ratio as well, is really all that it's saying. Now, the good news is generally when we take derivatives, it tends to simplify expressions, which means this result may be easier to calculate than the original. All right, let's just take a look at a couple of very simple examples of this. So let's say we said, I said find the limit as x approaches, I don't know, let's do 3, x squared minus 9 over x minus 3. Now, like always, just like back in Calc 1, whenever we first did limits, the first thing you always want to try to do is direct substitution. Now notice if we do direct substitution here, we get 0 over 0. Now back in Calc 1, that generally told us, hey, we got to do some algebra, some simplifying to figure out what that value actually equals. But here we actually have another tool to help us, because since we have this indeterminate form, and it is one of the forms that we can do L'Hopital's rule with, I can say that this limit is equal by L'Hopital's to the limit as x approaches 3 of the derivative of the top divided by the derivative of the bottom. Now, as soon as you actually do L'Hopital's rule, you want to try direct substitution again. Now notice this time, if I just plug in 3, we get our 6. Now, let's go back real quick. You wouldn't need to do this, and that's it. You're done. That quick and that easy. Now, back in Calc 1, the way that we had to do this, the limit as x approaches 3, we would have to factor the top, that's the difference of squares, over x minus 3. you can see that our x minus 3 cancels, so this is limit as x approaches 3 of x plus 3, which by direct substitution is 6. So you see we do get the exact same answer that we had before. All right, let's try another example. What if we did something like this? The limit as x goes to, let's say, infinity, x squared plus 5x minus 2, x cubed plus 2x squared minus 4. All right, so here we're taking the limit as x goes to infinity. Now, remember a couple different ways that you can interpret this. Here we're talking about the end behavior of this because we're saying as we head out towards infinity. Another way you may interpret that is we're looking at the horizontal asymptote as we head out to positive infinity. But still, back in Calc 1, the way that we would do this is trying something like direct substitution. And you can see on the top we're going to have infinity squared. Down here is going to be an infinity cubed. So that's definitely infinity over infinity. Back in Calc 1, we had a method to help us do this, and even way back in algebra, we had a way to think about how to do this. But now that we have this indeterminate form, let's try L'Hopital's rule, because we have an infinity over infinity. Well, that says this will be equal by L'Hopital's. The limit as x goes to infinity. The derivative of the top, 3x squared plus 4x, divided by the limit of the bottom. And then you try direct substitution again. But if you notice we do direct substitution again, we're still going to get infinity over infinity. Now the good news about L'Hopital's rule is this can be continually applied because now we basically have a new limit that we want to find. So we can keep doing L'Hopital's rule as long as we continue to get indeterminate forms. That's why you always want to check direct substitution after that. So let's try it again. This is going to be the limit. So we go to infinity, the derivative of the top over the derivative of the bottom, and then we try direct substitution. Now doing direct substitution this time, notice we're got a 2 on the top, and of course the bottom is going to go to infinity, which means that is 0. Okay, so you can continue to do L'Hopital's rule as long as you want, as long as you continue to get an indeterminate form, or to say, an indeterminate form. So as long as you're getting a 0 over 0 or infinity over infinity, you can keep doing that. All right, let's try another example real quick. Let's get this out of here. Let's take a look. If I said, what is the limit as x goes to 0, let's say from above, of x natural log of x. Now, just for a little subtle hint here, why would the limit have to go from 0 from above? Well, think about what the graph of the natural log of x looks like. It doesn't exist for values less than 0, so we have to come in from the right-hand side. All right, if we do direct substitution, well, that's easy enough to see that that's 0, but what is the natural log of 0? We know the logarithms don't exist at 0, but again, the graph's going to be something that really, really helps you here. So we know at 0 we have a vertical asymptote, and we know the graph looks something like this. So as we approach 0 this way, we can see the graph is heading down. So here we get 0 times negative infinity. Okay, so what's 0 times infinity? Again, that's one of those values that doesn't even make sense. Is it 0 or is it infinity or something in the middle? Who knows? Well, this is not an indeterminate form, right? We have to have a ratio here. But anytime you have zeros times infinities or stuff like this, you can always kind of cheat and make this work. To do this, take one of your two functions, and it doesn't matter which one you do, and kind of roll it down to the bottom. I'm going to take the x down there and write it as 1 over x. Right? Now you can see this is the same thing, right? Because if we divide by a fraction, we multiply by our reciprocal. Now if we do direct substitution this time, as we approach 0 from above, that's negative infinity. And as we approach 0 from above, that's 1 over 0. That's also heading towards infinity, but since it's positive, it would be positive infinity. Well, there's our indeterminate form, right? We have an infinity over infinity, so L'Hopital's rule here should work. So we can say this is equal by L'Hopital's, the limit as x goes to 0 from above. Now it's going to be the derivative of the top, so that's going to be 1 over x all over. Remember, 1 over x is really x to the negative 1 power, right? So the derivative of this, bring down the power, take 1 away from the power, will be negative 1 over x squared. All right, so if we do direct substitution right now, well, we know the limit as we go to 0 of 1 over x is going to be positive infinity. Same thing's going to happen here, that this is still going to go to positive infinity, but we have a negative out front, so that is negative infinity. So does that mean that we should do L'Hopital's rule again? Well, we could, except we shouldn't be able to notice that, you know what, I'll bet you this expression here would simplify a little bit first. So let's actually do a little bit of algebra. Now notice I'm not doing L'Hopital's rule again, I'm just going to do some algebra here. I'm going to write this as 1 over x times negative x squared over 1. Well, that's the limit as x goes to 0 from above. We end up with negative x when that reduces. And of course, as that goes to 0, we get 0. Okay, so if we end up with one of these indeterminate forms where it's 0 times an infinity, you can always take one of the functions, kind of flip it down in the denominator, then you can use L'Hopital's rule, because that'll either give you 0 over 0 or an infinity over an infinity. Remember, every time you do L'Hopital's rule, if there's an easy way to simplify it to get to a result, you do want to do that. All right, so there's another type of indeterminate form we can deal with, but there's also others. Now, the other ones are going to require more work for us to actually get it into a form where we can actually do L'Hopital's rules. So let's take a look at this. Other indeterminate forms. Now, these get a little weird. What I mean by get a little weird is we got to talk about them a little bit. Something like this. What would 0 to the infinity power be, or infinity to the 0 power be? What about 1 to the infinity? Does that even make sense? Now remember here, these are all limits. And here's where it gets a little fuzzy. What is 1 raised to the infinity power? Well, the answer to that is 1. If it is exactly the number 1, times itself an infinite number of times will give you the 1. But remember, here we're talking about limits, which means most of the time this thing's going to be the limit as we approach something is going to be approaching 1. So if this is approaching 1 down here, this is not 1. If it's exactly 1, then it is 1. So it's a little tricky there. So we have these other indeterminate forms that may deal with exponents, and again, you know, you can come up with a lot of these. What about 0 to the 0 power? You know, anything along those lines, infinity to the infinity power. These are all basically going to be slightly different methods for us to get to do L'Hopital's rule. So let's start out with something like, what if I said find the limit as, let's go x goes to 0 from above again, of x to the 1 over x. Now, if we try direct substitution, this is going to be 0 to the 1 over 0. Now, remember, we're heading towards 0, so it's really not 1 over 0. So this is 0 to the infinity power. All right, so this is one of our other indeterminate forms. To generally do these with exponents, the idea is we need to get that exponent down so we can deal with it. So what we're going to do is let's go ahead and say we think this is going to have some value. And I'm going to call the value of this limit y. So whatever the answer is y. Now to get the exponent down, I'm going to use logarithms because the property of log says if you have the log of something raised to a power, you can bring it down. So I'm going to take the natural log of both sides. And as x goes to 0, so 1 over x. And the good news, one of our properties of limits is limits can pass inside and outside of any continuous function. So I can actually bring that limit out here. When we first saw it, it was actually the other way around. It could pass into continuous functions. That was way back in Calc 1. That's going to be the natural log of x to the 1 over x. Okay, so the reason we do the natural log is so now we can bring down that exponent. So I get the natural log of y is equal to the limit as x goes to 0 above 1 over x times ln of x. Okay, if we do direct substitution here, what are we going to end up with? Well, direct substitution, I'm going to move this up here so we got a little bit more room. We got natural log of y is equal to, well, as we go from 0, from above of 1 over that, that's going to be positive infinity times, and we knew what this was from a few minutes ago, that would be negative infinity. All right, now is this an indeterminate form? Do we know what positive infinity times negative infinity is? And the answer is actually we know what that is. We know what a positive times a negative is, so no matter what, I know that that's going to be a negative, and infinity times infinity is infinity. Well, we're not done yet because that tells us what the natural log of our answer is. So to get to our answer, just exponentiate both sides. So y is equal e to the negative infinity. Of course, e to the negative infinity, if you wanted to rewrite that, that's 1 over e to the infinity. 1 over infinity, which is 0. So the limit as we approach 0 of x to the 1 over x, because that's what we said y was, is 0. Okay, so if you have an exponent in one of your indeterminate forms, taking the log of, setting it equal to a value, then taking the log of both sides so you can bring down that exponent is very, very helpful. All right, now this actually gets us to another way to represent one of our universal constants. Let's take a look at, let me get one down there, one of our more famous limits. Let's do the limit as x goes to 0. 1 plus 1 over x to the x. Actually, let's go to, I got it backwards. Let's go to infinity. Okay, so if we do direct substitution here, now this is where it gets a little tricky and you really got to pay attention to what's happening. We do direct substitution, I get 1 plus 1 over infinity. Well, 1 over infinity is 0, so on the inside that's going to be a 1, and that goes to infinity. So it'd be very easy to say, well, 1 to the infinity is 1, so this limit is 1. Well, you'd be wrong, because the limit's not 1. We'll see what it is here in a second. Because this on the inside is not exactly 1. Remember what I said a few minutes ago? Exactly 1 raised to the infinity is 1. That's true, but this isn't exactly 1. This is 1 plus something that's infinitely small, basically. So it's 1 plus something. All right, so another way to think about this is 1-ish to the infinity is not 1, but 1 to the infinity is 1. Okay, so how would we do this? Well, we got this weird exponent thing again, so we're going to do the same method that we just did. Let's let this be equal to some value. Limit as x goes to infinity, 1 plus 1 over x to the x. We're going to take the log of both sides, log limit x goes to infinity, 1 plus 1 over x to the x. The log can pass through that limit, so limit x goes to infinity, log 1 plus 1 over x to the x. Now remember, the reason that we do this is so that we can bring down that exponent. So this is the natural log of y is equal to the limit as x goes to infinity, x times the natural log of 1 plus 1 over x. Now once you do that, go ahead and see if you can apply this limit now. What would we end up with if we did just direct substitution? Well, that would be infinity times, well, this is going to be 1 plus, again, that goes to 0. So this part here would be the natural log of 1. The natural log of 1 is 0. All right, that's both good news and bad news. We don't know what that is. Remember, that's one of our indeterminate forms. But we did see just a few minutes ago, where if we have infinities times zeros, we can always take one of these two functions and flip it into the denominator. So we can get a ratio and do L'Hopital's rule. All right, so let's see here. So I'm going to take the easier function, the x, and flip that down to the bottom. So I'm going to get the limit as x goes to infinity, the natural log of 1 plus 1 over x, all over 1 over x. Right, all I did is I took this x and kind of flipped it into the denominator. Now if we do direct substitution, you're going to see that we get 0 over 0. Right, we already knew the natural log of 1 was 0, and now 1 over infinity is 0. So now we can do L'Hopital's rule. So this is the natural log of y is equal by L'Hopital's to the limit as x goes to infinity. All right, the derivative of the top divided by the derivative of the bottom. That's going to be a little ugly looking. So remember, this is going to be the derivative of a log is 1 over the argument times the derivative of the argument. So the derivative of 1 plus 1 over x, derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. Remember, that's x to the negative 1. Same thing in the denominator. The derivative of 1 over x is negative 1 over x squared. All right, now I could try to evaluate that, but if you notice, we can do some arithmetic first. So this is just equals. I'm not doing L'Hopital's rule, just doing algebra. The negative 1 over x squared cancel, and I get 1 plus 1 over x. Now that we've simplified the expression, let's try to simplify this. Can we do the limit now? Well, as x goes to infinity, that's 1 plus 1 over infinity, 0. So this answer is just 1. All right, that doesn't give us what our original limit is. This gives us the natural log of that. So all we got to do now is write this in exponential form, or exponentiate both sides. So y is equal to e to the first, or y is equal to e, right? Our number e, which means from way back in the beginning, we have a new definition of our number. It says this, it says the limit as x goes to infinity, 1 plus 1 over x to the x is e. Now, you can do this again, and I highly suggest maybe that you try it. You can actually prove this very easily, that the limit as x goes to infinity, 1 plus a over x to the x is e to the a. All right, so basically you just run through this again, replace this 1 with an a, any number, and see what you get. You're actually going to end up with that expression there. So we end up with a basic definition for one of our universal constants here based off of a limit. So L'Hopital's rule is a very, very useful rule, but the things you got to watch out for are, is it in the right indeterminate form to do L'Hopital's rule, 0 over 0 or an infinity over infinity? And if it's not in that form, you can't do L'Hopital's rule, but there may be tricks, like flipping things in the denominator, to get it into this form. Now, there are a couple other air quote indeterminate forms that you might run into. There's really only one more, but let's get this out of the way. Just a few things. Is infinity times infinity indeterminate? No, it's not. We know what that is. That is infinity. What about infinity plus infinity? Is that indeterminate? No, that's actually determined as well. If you have an infinite number of things, you add an infinite number of things, you get an infinite number of things. The one more type of indeterminate form that you're going to run into is this. What about infinity minus infinity? If you've got an infinite number of things, and I take away an infinite number of things, how many things do you have? Well, you don't know. So here's a quick little hint. If you have infinity minus infinity, that means you have two terms or two pieces. L'Hopital's rule is all based off of one ratio, right? One number over another number. So if you ever end up with an infinity minus infinity, get those two expressions together, get a common denominator, whatever it is, get them together so you can have one expression. This is indeterminate. All right, that's the only other indeterminate form that you're going to run into, and there's not much of a trick. Just put it together as one expression, and then it should fall somewhere into one of the methods that we've seen before. So, very helpful technique. It's a lot quicker than some of the things we did in Calc 1 with the algebra, and we're able to do a lot of expressions that we couldn't do in algebra and Calc 1.